Okay. What an auspicious start. Hi, everybody. Next topic here. And our discussion of the second law of thermodynamics is really the third law of thermodynamics. It's covered in Atkins 3C. And I'm going to start with a weird place, or really a weird question, which is here. Right? What does entropy mean to a molecule? Not an obvious answer. When you talk about energy, I can relate energy to the kinetic energy of a molecule and how fast it's moving. But entropy, I don't really know. And here's how you might start to think about this. Ignore this for a second. Imagine three molecules, we'll call them A, B, and C, which have a total energy of 3 energy units. We'll give it the symbol epsilon. If the molecules have available energy levels 0, 1 epsilon, 2 epsilon, 3 epsilon, et cetera, et cetera, et cetera, how could these molecules be arranged? Here's one possible answer. I could put molecules A and B in the 0 energy level, and I could put molecule C in the 3 epsilon energy level. Total energy of 3, and this works. But there are other ways I could put the molecules into this configuration as well. Right? I could do this. I could put molecules AC in the 0 and B up top, or BC and A. All 3 of these configurations are consistent with this energy. There's more, right? Rather than 2 in the 0 and 1 in the 3, you could do something like this. You could put molecules A, B, C all in the 1 epsilon energy level and have a total energy of 3. This works. There's one more arrangement, and it's something like this. I put molecule A in the 0, B in the 1, and C in the 2 epsilon. And then you go through and you do all the permutations of this arrangement. And you'll see that there's actually a total of 6. There are 6 possible ways that we could arrange these molecules. And now I can ask this question. Which one of these configurations is most probable? And I don't know if that's obvious to you, but let me show you the answer. Right? The answer is this one. This arrangement is the most probable. Why is that? Well, it's simply because it has the most number of outcomes. There are 6 different ways that I can set the system up like this. The mathematical term for that is a weight, right? W equals 6. Contrasts with this one. Right? There's only one way in which I can equally divide the energy. 6 this way, it's a lot more likely. And so the question then is, how does this weight, the number of ways that we can divide up a system, relate to entropy? And the person who figured it out is this guy, Ludwig Boltzmann, one of the great physical chemists of all time. This is his grave. It's in Vienna. You can go see it, and you can actually look at his formula on his grave. Okay? If you get a formula on your grave, it's pretty important. Side note, if you want to look up other scientists who have equations on their grave, you can do that. You might be surprised. Anyways, what is Boltzmann's formula? Well, Boltzmann's formula relates entropy S to this weight, right? Or what he called the number of microstates. And specifically, the formula is here. S equals K natural log W. If you're paying really close attention, you might say, why did it say log on his grave? The answer is log is European for ln, right? What we call ln, but the Europeans call it log. So these formulas are the same. And the new thing here is this constant Kb. We actually saw it briefly in the context of the equipartition theorem. It's simply a constant, a molecular version of the ideal gas constant. So it's 1.38 times 10 to the minus 23 joule per Kelvin. This formula relates entropy to the number of microstates. It's telling us what entropy is to a molecule. So to tie this all together, here are some different definitions of entropy, and you've seen these at different levels of complexity. In Gen Chem, when you talked about entropy, you just talked about it likely as chaos or randomness, right? Things are all over. What we previously developed was this definition, delta S equals Q reversible divided by T. This would be a macroscopic definition. Right? These are all things that we can measure, Q, temperatures, et cetera, et cetera, et cetera. This is the microscopic definition, right? What entropy means to a molecule. And what I said is the following. It relates to the number of ways that molecules can be arranged in a given energy state to produce a certain total energy. When the universe seeks to maximize entropy, it is maximizing the number of ways in which energy can be shared. It's maximizing the most probabilistic outcomes. So that's what entropy is to a molecule. I can't help myself, but I want to give you one brief interlude here. So one of my sort of pet hobby interests is information theory. If you're feeling extra nerdy and want to talk about information theory, come talk to me. But entropy is really important in the context of information theory. And the first person to actually connect this was Gil Lewis. He's the same guy who Lewis structures are named after. And what he said in the 30s was that an increase in entropy corresponds to a loss of information, nothing more. When I often think of entropy, this is what I think of it as. When you increase entropy, you lose information. And this is just one example of it. Again, we have one gas molecule in our two-sided, two-bulb gas arrangement, like we saw with the free expansion. Right? If you remove this partition and the molecule spreads out, the entropy increases, right? The volume has increased, but you've lost all the position information. So sometime after that, in the 40s, computers started being invented, really at IBM Labs here in New York. And one of the first people to think about the mathematics of it was this guy, Claude Shannon. He wrote this really important paper called A Mathematical Theory of Communication. And what he recognized was sort of the opposite process of what Gilbert Lewis was talking about. He said, if I start in this region where I have 100% uncertainty about where this particle is, and then I somehow locate it in one of these two compartments, I could think of those compartments as 1 and 0. I now know with 100% certainty it's there, and what I've generated is one bit of information. So he was thinking about how to describe all of this and the mathematics that might describe this, and specifically he was trying to think of a name for this type of relationship. And this is what a friend told him. He said, you should call it entropy for two reasons. First, your uncertainty function has been used in statistical mechanics under that name, so it already has a name. And second, and more important, no one knows what entropy really is, so whenever you talk about it, you'll always have an advantage. Good to keep in mind. Okay, how does any of this relate to the third law of thermodynamics? Get to the point you're saying. Here's the question. How many microstates are available at absolute zero? How many different arrangements could exist at absolute zero? You sort of start imagining this and you condense it down so it has no energy, and what you'll realize is that there's only one. There's one theoretical microstate weight at absolute zero. And if you plug 1 into Boltzmann's formula, the natural log of 1 is 0, and you'll predict that the entropy is 0. And in fact, this is the third law of thermodynamics. The third law of thermodynamics says the entropy of a perfect crystalline substance is 0 at T equals 0. That's the third law of thermodynamics. It actually wasn't developed from Boltzmann. It came out of a series of other observations, and I briefly listed them here. The first is called the heat theorem. So what people were looking at was the change in entropy as the temperature got lower and lower and lower. And what they realized was that this change in entropy got smaller and 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 smaller, and it looked like it was approaching 0. The second is something called the Debye approximation. And what Debye recognized was that the constant pressure heat capacity, CP, scaled as temperature to the third power. And the temperature was close to absolute 0. So CP equals A times T cubed, where A is some constant. And this became important because it allowed people to very accurately calculate entropies. All three of these ideas, the Boltzmann formula, the Nernst heat theorem, and the Debye extrapolation, are all consistent with the third law of thermodynamics. Why do you care about any of this? Well, it will end up being important when we calculate entropies of reaction. So if the entropy of a pure substance is 0 at 0 Kelvin, it allows us to calculate absolute entropies. When we have energy functions like change in H, we talk about a delta H. But when we talk about entropy, we talk about the absolute entropy. The second, and this is I think more of an interesting idea, is that if that is true, if the entropy of a pure substance is 0, it turns out that we know that it is impossible to experimentally achieve absolute 0. Okay? There's no way you can ever get there. And I did some looking. This is the lowest inferred absolute 0 temperature that anyone's ever made. So it was done in outer space. And they had some spectroscopic data that looked like things were at 10 to the minus 15 Kelvin. Close to 0, but not quite. Okay, I'm going to stop here and we'll talk about free energies next time. See you then.